All right. Let's go over a few sort of housekeeping items. I already talked about the papers. I've returned your first test to you, didn't I?
Yes, sir.
Okay. Still waiting on the second test. Am I not?
Yes, sir. Oh,
okay, that's all right. Okay. All right. You've turned in your paper. I'm waiting on yours. Okay. Have you done the student course evaluations?
Where?
Huh?
Where's that at?
Is okay. There's two ways you can do it. Do you ever check your Lawson email?
I can. I don't really anymore.
Okay. If you check your Lawson email, you'll see sometime probably 3, 4, 5 weeks ago, something like that, somebody sent out an email that has a link. You just click on the link, you go straight to the evaluation. That's the quickest way. Now, if you can't get in your email or forgotten how to get in your email or don't want to go back and find it, you can go to the Lawson State webpage, right? And on the Lawson State webpage, there's a bunch of blue tabs at the top. But over near the right, there's a big yellow tab, a gold tab, and it says Quick Links. If you click on Quick Links, then you get a huge screen and you scroll through it until you find something that sounds like surveys. I think that's what they call it, surveys. I haven't looked at it this term to see if they changed the name, but I believe it's surveys. If you click on that, then it gets you there too. So either way, but please do the student course evaluations. They are on us like stink. Anyway, to get these done, and they want 80% or better in every class. And guess what? 3 people in the class, that's going to take all 3 of you to get better than 80%, right? So, Lauren, do your student course evaluation too. And y'all do yours too. Please get those done. Okay? What's that?
When did they send it?
It was several weeks ago. Also saw an email in there, you won $1 million, but the deadline's passed. Okay. Did you find it? They did another one today? I can't hear what you're saying.
Yeah,
you found it? Okay. All right. You don't have to do it right now, but you know how to do it now, right? Okay. Good deal. All right. You also are going to vote next Tuesday, right? Either before you come to campus or before either before, after 7 in the morning, before 7 in the evening. So for 12 hours. You're going to find the time to vote, right? Yeah, please do. All right. What else? I'm going to give you, at the end of the class today, I've got to run them off, your last test. And you can get if you haven't yet turned in a paper, if you get it to me today, you don't lose any points, okay? If you get it to me after today, you start losing points. The sooner, the better. Oh, yeah, and you've emailed me yours. That's right, you said that. Okay. Your tests, get them to me as soon as you can. And let me just tell you where I'll be and when, okay? I'm on campus today and tomorrow, all day. My office hours today are 3:15 to 5:15. No, sorry. Yeah, that's right. 3:15 to 5:15. Tomorrow, my office hours are 1:15 to 3:15. Now, if you do come and turn it in, and I'm in class or something like that, you can slide it under my door. Both of you know where my office is. Okay, 265. Okay, you can slide it on my door if you can't see me or catch me somewhere. Okay, Friday I'm on the Birmingham campus, and that's 7:45 to 11:45. Birmingham campus, Dr. Pruitt's office. You know where that is? You don't. You know the B building, the big long building? Okay. When you come in from the ball field end of it, you either go down half a flight or up half a flight. Go up half a flight, right? When you get to the top step, immediately on your right is 122. That's Dr. Pruitt's suite of offices, and his name and Ms. Saxon's name are on the outside there. my office is the copy room behind the sections desk. I'm there on Fridays. Okay, so if you are going to turn in something on Friday, that's where I'll be. 7:45 to 11:45. Okay, and if I'm not there, the section can take it and give it to me or whatever. Okay. Now next week, finals week schedules are sort of wacko. Okay, 8 o'clock tomorrow, Monday morning. Okay, I'll be doing a review session in this room for my Math 100 class. It goes 8 to 9:50. Hour and 50 minutes, not hour and 15 minutes. Okay. Once that's over with, the rest of the day, I'm free. Okay. So I'll either be in my office or I'll be giving makeup exams. Makeup exams, I usually start at my office, try to find the closest empty classroom to my office, and that's where I do makeup exams. That way I can go back and forth to my office easier, may even be able to hear the phone ring, you know, that kind of stuff. So so after 10 o'clock on Monday, 8 to 9:50, I'm up here. I can't really answer any questions or deal with anything. You can slide something under my door. But after that, say 10 o'clock on till 5:15, I'll either be in my office or in some classroom in between my office and here. Okay. Tuesday, I have an exam in this classroom, 8 to 9:50. Okay. So if you want to come turn something in, I'll be up here giving an exam. So that will be fine. After 9:50, I'm in my office or in a classroom in between here in my office from 9:50 until 3:15. But I have a second mini-term physical science class, and mini-term classes, they have class next week, okay? So I'll be in class from 3:15 technically until 7:45. I think we will finish everything well before 7:45, but after 3:15 for the next few hours I'll be up here in class. So it's not a good time to get in touch with me, but you can leave something on my door or turn something into me. That will be fine. Now, like I said, we'll probably finish before 7:45, so I'll be either in my office or in some room in between them. All right, that's Tuesday. Wednesday, I have nothing scheduled, but that doesn't mean I won't be giving makeup exams and stuff. So again, either in my office, 265, or some classroom in between there, here or there. Okay? Thursday, nothing scheduled from 7:45 in the morning until 3:15. Now, technically, 3:15 is when that physical science class has their finals, but I'm allowing them to take it early if they want to, because a lot of them are automotive students, and this may be the last final they have, and they just have to sit around. Some of them from out of state, some of them from all over the state, so they don't want to sit around for 4 days and take the final on Thursday afternoon. So I'm giving them the option of taking it early. So that's why I may be anywhere in between here and there, giving an exam any day. So if any of them do choose to take it, not all of them are automotive students, if they do choose to take it, it'll be in this room at 3:15. And it won't take them more than 45 minutes to do it, so I don't think so. I'll be here probably till 4 o'clock and then back in my office or somewhere in between. The next Friday, again, I'll be on Birmingham campus, 7:45 to 11:45. All right. Now, you have both been here a while. You know that during finals week, you cannot access Student Suite. You remember that? Okay. You can't, because our ancient system we have only has like 16 or 32 portals. That's all. So during final exams, when all students are trying to check their scores, we can't get in to put the scores in, you know, the grades in. So they shut students out of the Student Suite during finals week. But what you can do is go to Blackboard. It's always open. And I always put and most people do, put the grades in Blackboard before we put it in the Student Suite anyway, or in the suite anyway. So check Blackboard during finals week, check Blackboard, you'll be able to see everything. All right, grades are due, and usually it's the 12 noon on Monday after finals week is over with, okay? Last term, it seems like they gave us an extra day and made it Tuesday at noon. I think they have some glitch in the system or something. So whatever day it is, I have to have grades in, so please get everything to me next week, because I may have to have grades in by noon on Monday. And if so, if I don't have it That's an incomplete, and you have to clear the incomplete. So please get me the stuff. All right. Hope, Lauren, you were able to follow all that. Yes?
Do you want us to turn the test 2 in before the other one, or can we just turn them together?
Either way. Sooner on either one of them, the better. The sooner I can get them in, the sooner I can get them graded. And I don't have as much stacked up at the end. I prefer not. Okay. Yeah, but yeah, if you want to turn, if you only want to go make one trip to campus, you can turn them both in. Okay. All right, good deal. Any other questions? Okay. Okay. Now, I believe that's all. It seemed like there was something else, but I don't remember what it is now. I think with my bigger classes, I give more announcements, but not this one. Okay. Where we were last time was on page 461. This is chapter 8, further application of integral, and we're not doing Taylor polynomials. 8.3 was center of mass, and theorem 2 at the bottom of the page is the theorem of Pappus. And for the life of me, I cannot find that on the slide set, okay? So I'll just sort of write it in here. Do both of you have your books? Or you got an e-book? Okay. Well, I won't write it then if you have it. If R is a region in the plane of area A, okay, let's just imagine it was something like that. Region in the plane of area A. And we rotate that about an axis that is disjoint from that region R. So in other words, the region R cannot be, the axis cannot be here, because that would be touching. It could be right at that tip, or at this tip, or that tip, or it could even be that line. And you're going to rotate this. Or the axis could be over here, over there, up there, here. And you're going to rotate that entire region about that axis. Okay? That's what you're doing. Okay? Then the theorem of Pappus says the volume of the resulting solid is the product of your area A that you knew or you could calculate with the distance traveled by the centroid. Okay? So, if you had found the centroid of this area, assuming it's a laminar plate, find the centroid. Okay? And let's say you're rotating about an axis here, that distance here, the distance traveled would be 2 pi r, where r is the distance between the axis and the centroid. If it was over here, then it's the centroid here, that would be the x component here, the difference here. Up here it would be the difference in y. So the distance the centroid travels times that area. That would be the volume. So it's sort of like we did with surface areas, you know. If you had a surface area, revolve that around. This is just using the centroid. It makes things a little bit easier. Okay? That's the theorem of Pappus. And they do have a little proof on it. Knock yourself out. Okay. Now, I don't know why it's not showing up, because I thought this was in the old edition too, but they're not showing either one of the slides on that. Okay? What they do show is this, which is a pretty neat thing itself. And there's a little historical blurb here on Archimedes. And many people consider, and I think this is probably pretty true, Archimedes right up there with Newton and Euler, who you wrote your paper on, right? Some of the top mathematical minds ever to grace the planet, okay? The thing is, Archimedes did his stuff way BC, okay? 287 to 212 before the Christian era, BC, before Christ. Way back there. And incredible mind he had. And of course, then Newton came along, what was it? 14, 16, 1700, something. Yeah, okay. but AD for sure. And then Euler was within a century or so after him. So those are modern guys. Archimedes, way back then. And one of his things was the law of the lever, and this is the one illustrated here. And this basically is your center of mass, right? You put the fulcrum at the center of mass, and then the M1, L1, which is the mass 1 times the distance from the center of mass, is equal to M2, L2. And this is exactly what a lever is. Yeah. And there's several types of lever. Archimedes did this way before calculus. Way before calculus. Okay. So, both of you have already done your paper topics. That would have been a good one. Can't remember, Lauren, if you've turned in the paper or not. That would be a possibility. So that's all we had left. Do you want to do the preliminary questions for 8.3? No? No? Okay. Homework exercises 8.3. I probably have assigned these already. Any of the odds, 1 through 9. Any of the odds, 11 through 17. Do 19. Any of the odds, 21 to 25. Do 27. Either 29 or 31 or both. And then any of the odds, 33, either 33 or 35 or both. 37 or 39 or both. And then try to do 41. Okay, good deal. Any questions? I think both of you done. Sorry we're not going to get the Taylor polynomials. That would be another potential paper topic. Who in the world was Brooke Taylor anyway? Again, a pretty incredible mind in himself. He came up with these polynomials. Have you ever used a Taylor polynomial? Huh? I know. It's a rather strange-looking little character, isn't he? Okay? But have you ever used a Taylor polynomial? Taylor series? I'm certain you have. If you use the calculator, have you ever figured out how the Euler calculator works? Taylor series, basically, is what it's doing. It is the fastest, most efficient, I think, of just about any of the convergences you can calculate anything using it. This guy came up with. If you just thumb through the section there, we're not going to do it, you'll run into another Scottish mathematician, Colin Maclaurin, and he was almost a contemporary, a later contemporary. Their lives overlapped, but he did a lot of the same work too. Newton was so impressed with his work that he once offered to pay part of Maclaurin's salary. So there were some pretty good mathematicians right around that time. Pretty interesting there too. The Maclaurin series is a special case of the Taylor series. Okay. So we're not going to do anything there. Again, chapter 9 is differential equations, which is a completely different course, and y'all are both taking that at your home campuses, right? Or something. No. Well, okay. Are you? Is a chance you're going to come back here and do differential equations, or are you going to take that?
Differential equations. No. I'm not sure yet.
Okay. Okay. Anyway, it's a completely different subject. And by the way, in that, there's Euler's method. He approximated differential equations way back. What's that?
Maybe teaching in the summer.
Okay, I probably will be teaching in the summer, but anyway, we're not doing that here. That's a different course. So we're moving now to, if I can get this to end. There we go. All right. All right. Moving now to chapter 10. All right. Second. It's on page 513. Do you find the e-books tough to navigate?
Well, mine I got it for free.
Uh-huh.
So I just downloaded a PDF online. So
Uh-huh.
I mean, it's all right.
So, all right.
It's like when I took pre-cal, I had the book itself and the ebook. But when I was doing homework, it was easier to use the book itself
Uh-huh.
to look at it. But I had to do website.
Right.
It was
Website what?
hard.
Okay. It was fun though, wasn't it? I found it absolutely obnoxious. Huh?
Yeah, I still have to deal with physics.
Uh-huh.
It's so hard. The questions on there are harder than any of the ones we did in class.
Actually, I remember back, trying to remember the name of it, but physics was one of the first subjects that came up with the online assignments and stuff like this. It had a name, and I think WebAssign stole stuff from that and built it. So they may actually have originally been the same company, but it actually, I think, started with physics and then later moved to math and other things like that.
And you know how we talked about like the answer has to be exactly right? I had one the other night that was like, it was something 0.333333. So I just put that 0.3 and I was like, no, what did I do wrong? And I tried to rework it. I went back and put one more 3 and it said it was right. So like, I mean, I had the right answer. I just,
Right.
33333. I was like, okay, I just 1 3 is fine.
And that can be so frustrating now. But was that in physics?
Yeah.
Physics does pay a lot more attention to significant digits.
Yeah.
So probably you were a little, you hadn't done as many as you were allowed. So that's more precise. But in this, I mean, where you could have 4x plus 3x, or x times 4 plus, I mean, that's not right. 4x squared plus 3x, or you could do x times 4x plus 3. Both of those are perfectly correct answers. Neither one of them is preferable to the other, but it's only going to recognize one. Okay, and it just aggravates the fool out of me that says, no, it's wrong. When it's not wrong, it's correct, but it's just not the one they were looking for. And in calculus, goodness gracious, there's so many different ways you can express an answer that are perfectly fine. All right, so let's move on to this. This is not the figure that's in your text. This is I'm pretty sure it was a Hubble Space Telescope photograph here. Our knowledge of what stars are made of based on the absorption spectra, which is a sequence of wavelengths absorbed by gases in the star's atmosphere. And it's a pretty picture and has really fairly little to do with that. But that's probably an area of space where a lot of stars are either in the format or in the process of being formed. Okay. One in your book is a series allows us to make sense of a process that iterates infinitely as occurs in fractals, which generate pictures such as the one there. That's not a picture of anything. It's a computer-generated thing. You're just doing the same thing over and over and over and over and over again, but in a somewhat, a little bit of a randomness to it, but you can see it's not completely random. The things, same shapes show up, they just vary in size. That all deals with infinite series, which Taylor's series is going to be at the end of this section too, but we're not going to get there. Here's an example. It actually calls this the infinite series. Theory of infinite series is a third branch of calculus. You have differential calculus, integral calculus, and series. Okay? And by the way, good old Isaac Newton did all three. Everybody talks about the first two. He did the third one as well. Okay? I can't recall if, what's his face, Leibniz did or not, but Newton, I'm pretty sure did. All right. For instance, this is a Taylor series, though they're not telling you that yet. What can you tell me about the function e? Anything? That function e to the x. What is e anyway? It's what? It's the base. It's the base for the natural number system. You know why it's named e? Yes, named after him. He's the one that came up with it. Yeah, it's actually pronounced Euler. Yeah, I did too first, and then finally I saw a phonetic thing of it. It's like, oh, it's Euler. It's not Euler. Okay. It's an irrational number, and you're raising an irrational number to a variable power. Yuck! It's a mess, except it's not. It's a very simple thing, and here's how you calculate it. And this is how your calculator calculates it. It's 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus ... Keep on trucking. Okay? Does anyone know what e is, that number? Do it on your calculator. E to the 1. See what you get. 2.718. Keep going. 28. 28. Is that all your shows? Does yours show anymore? Did you stop there too? That's unfortunate because it looks like it's repeating that 1828, 1828. It doesn't. The next digit is nowhere close to 1828 yet. It just happens to be those 4 digits repeat once, and that's all. It's not a repeating decimal. If it was, it wouldn't be an irrational number. Okay, now I want you to do this. That's e to the 1. Okay? Second? After the last 28? 4, 6? So you see it's not repeating. Okay. I knew it wasn't, but I wanted you to see that it was. Okay, what I want you to do is do a 1 plus 1. Really high level math today. That gives you 2, right? Plus 1/2. That's 2.5. Plus 1/6. What you up to now?
8/3.
Second?
8/3.
Second?
2.6.
2.6. Okay, plus 1 24th.
2.7.
Okay, look at that. Plus 1 1/20th.
2.716.
Okay, you're up to that. Good. Plus 1 720th.
2.7181.
Okay, so you got through this digit. You just keep on doing what I had done x to the 5th over, because x is 1, that's what it's always numerated. Okay, for the 5 factorial, 6 factorial, 7 factorial, 8 factorial. And in no time at all, a little bit of time, you would have all these digits. And that's how your calculator did it. Only it did it much faster than I did. Okay. Now, let me first ask this. Do you know what factorial means? 4 factorial.
I've heard of
We did it. We did it last week.
It's 4 times 3 times 2 times 1. Yeah, right. Yeah, that's what it means. It's factorial. 4 times 3 times 2 times 1. So that's what I was doing. This is a 2 here. A 2 times 3 was 6, and 3 times 4 is, 6 times 4 is 24. 24 times 5 is 120, and times 6 is 720. Times 7, whatever that was. I can't do it in my head that fast, but you're just doing the previous one times the next digit. Okay. All right. Now, how about this? pi fourths. Pi is what? It's an irrational number, just like E. Okay, that's the first 5 digits, it's 3.1416, but it's an irrational number. So punch in pi on your calculator. Okay, divided by 4. Keep going. Second. 398. 163. 4. Okay, that's good enough. Okay. Now, they give here that pi fourths is equal to an infinite series, which is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13 plus ... Okay, keep on going. So, whoa. So you only use the odd numbers in the denominators and you alternate signs. So let's start that. 1, I know I can get that, minus 1/3. That would be 0.67, right? Okay. Plus 1/5. Okay, 0.86, so you overshot it. Minus 1/7.
0.723.
Okay, so you undershot it. Plus 1/9.
0.835.
Okay, you overshot it again. Minus 1/11.
0.744.
Okay, you undershot it again. Plus 1/13.
0.821.
Okay, overshot it. But notice every time you're getting closer and closer and closer. 1 over 100, 100, and you're ultimately going to get down to that. An infinite series. Okay?
How many numbers would it take?
I don't know. I was thinking it was going to converge a little faster than that, but it didn't. Okay, but it does converge over time. All right. Now, what we've done there are series. We're not going to do series yet. We're going to start with sequences. Sequences are these things we just did. For instance, the sequence of 1, 1/2, 1/6, 1, yeah, that's a sequence. Or 1, 1/3, 1/5, 1/7. A set of numbers is a sequence. Okay? Any set of numbers is a sequence. When you add, or alternate adding and subtracting, that gives you what you call a series. Okay? So a sequence is just a set, and a sum of a sequence is a series. Okay? So we're going to start with a sequence. All right. Let me erase what's on the slide here. And let's go to this. All right. This is starting with 1 unit plus 1/2 of a unit plus 1/4 of a unit plus 1/8 of a unit plus 1/16. Now, not plus. Just dividing it in 2 each time. This is a sequence. 1, 1/2, 1/4, 1/8. What would be the next? 1/16, 1/32, 1/64. That's the sequence. It follows a pattern. What's the pattern? The next number is always 1/2 of the previous number. Okay? That's the pattern. Okay? That's one form of a sequence. So that could be written as f of n, where n is what element in the sequence you are, and that would be 1 over 2 to the nth. Because when n is equal to 0, what's 2 to the 0? 1. 1 over 1 is 1. When n is 1, 1/2. When n is 2, 1/4. When n is 3, 1/8. Okay. So that is a shorthand way of writing that sequence we just put down, right? So a lot of times the sequence will have a shorthand notation that deals with n, which talks about the nth term in the sequence. Okay. So that leads you to a definition. They don't have the slides in order here, so I'll try to give it to you. All right. The limit of a sequence. We say that the sequence A sub n, okay? That means for our last one, that would have been a sequence. And by the way, that is a set notation. So we're talking about sets. 1, 1/2, 1/4, 1/8. That's the sequence. In that sequence, A sub n would have been 1/2 to the n. Okay? That's the shorthand for it. Converges to some limit L, and we write the limit as n approaches infinity of A sub n, is that limit L, or we just say an approaches L. If for every, boy, does this sound familiar, like Cal 1 again, right? For every epsilon greater than 0, there is a number, not a delta, but an m, capital M, such that the difference, when the difference between A sub n and L is less than that epsilon, you're going to be there for all n greater than that m. Okay? So you get big enough, and you guarantee that everything is less than that. Just like we were seeing with that plus minus plus minus plus minus, everyone was getting smaller. So just pick any epsilon you want to. Somewhere out there you can get that. From there on, you know it's always less than that. Okay? If no limit exists, we say that A sub n diverges. Okay? If the terms increase without bound, then we say that A sub n diverges to infinity. So there's two different ways to diverge. One, you just never converge, okay? Or you blow up, diverge to infinity. And we'll see examples of both of those, okay? Now, let's go back and zoom in here. All right. Here are a few general terms you could have, okay? If A sub n was 1 minus 1 over n, okay? Guess what n has to begin with here? Or what it can't begin with? It can't begin with 0, and don't ever go negative. And you could have a 0, not in this case. So this one can't begin any less than 1. Okay, so let's start with 1. And that's what we say, n greater than or equal to 1. 1 minus 1 over 1. 0. Okay, that's your first in the sequence. Okay, 1 minus 1 over 2. 1/2. 1 minus 1 over 3. 3. 1, yeah, 2/3. 1 minus 1 over 4. 3/4. 4/5. 5/6. Okay. You think that's going to converge? What are you getting closer to? 4/5, 5/6, 7/8. Yeah, it's getting closer and closer and closer to 1. That is converging to 1. That sequence converges. Okay, here's another. A sub n is equal to minus 1 to the n. All that's going to do is alternate signs. When n is even, that's going to be positive. When n is odd, it's going to be negative. And you're increasing by 1. This one can start at 0, by the way. Okay? And then if you're doing 1, so that would be 0. Negative 1 to the 0th power is 1, times 0 is 0. And when n is 1, this will be a negative 1, plus 2, minus 3, plus 4, minus 5, plus 5. Okay. You see? Is that conversion? No. Okay. It's certainly not converging, and it's getting bigger and bigger and bigger, but on either side, negative and positive. So it's diverging in two ways. Okay. So here's another one. Ooh, strange one, huh? This is no good when n is 2, right? Okay, yeah, that'll give you 0 in the denominator. So start with 3 or greater. Doesn't do any good to start less than because you'll run into 2 anyway. So start 3 or greater. Okay? Does that look at all familiar? You've had physics. Have you?
Something to do with a year.
The what?
Something to do with a year.
Year? Is that what you said? No, it's a Balmer series of the hydrogen atom, a model of the hydrogen atom, before the Bohr model, the Balmer model. And this is actually the spectrum of that you have for a hydrogen atom. This is a purple, I think, and then some reds, and then after a while, this actually does converge. Okay, oxygen starts big and then gets smaller, but it actually converges, and here's how you can tell. Divide the numerator and the denominator by n squared. Numerator becomes 364.5, right? That becomes 1 minus 0. Because 4 over n squared as n gets big, it's getting closer to 0. So this would be 364. So sure enough, you keep that dot, dot, dots going after a while, you get closer and closer and closer to 364.5. And you may not ever get there, but it's converging to 364. Okay? So those are just a few general terms. That's the Balmer series of a hydrogen atom spectra. Okay. Not that you need to know that. Okay. So this A sub n or B sub n, this is called the general term. Okay. Now some of your general terms. Oh, okay. Okay, we got a couple of examples here before we get to the next slide. All right, let's do them on here. It's not ideal. Example 1, and hopefully you've run into this before, but if you haven't, it's worth running into. It's a sequence, okay? The first number is 1. The second number is 1. Third number is 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. You see how that series comes about? Sequence comes about, not a series, sequence. What's that? No, not quite.
You add 0, and you add 1.
Okay.
And I'll be back at 3 to turn my paper.
Okay. And you're going to turn the next quiz. Okay. And you're going to do the next steps. Okay.
At 3. Will you be here at 3?
Yeah, I've got classes goes until 3:15. So after 3:15, I'll be at my office. I'll be up here at 3 o'clock, but I'll still be in class. But after 3:15, sometime after 3:15, I'll go back to my office.
Okay.
Y'all figured it out yet? You go flat. Huh?
The essay.
What about it?
The directions online.
It's what?
The directions.
Yeah, they're on Blackboard.
On Blackboard.
Yeah, on Blackboard under content, research paper instructions, but also if you go to the first YouTube video for the class, first or second one, you'll hear me talk about it there too.
Okay. Well, I get to YouTube. What they call it?
It goes to content. You go to Blackboard content,
YouTube video.
and the one of the things out there says Math 100 YouTube videos. Click on that. Okay. You're going to kick yourself. You're going to injure your foot trying to kick yourself. Okay. 1 plus 1.
2.
Okay. It's called the Fibonacci series. Okay. One of the most famous sequence, not a series, a sequence. Fibonacci sequence. One of the most famous sequences in the world. Okay. A bizarre one, strange one, but that, I guess you could have started with a 0 here, and then it would have been perfect. 0, but 0, 1, and that adds to be 1, that adds to be 2, that adds to be 3, that adds to be 5. Now, why is this so famous? Have you ever heard of the Parthenon? Okay. Very famous Greek building. Okay. It's one of the most beautiful structures ever built. It's a ruin now, but you can still see the beauty of it. Its dimensions were just about perfect. And it's perfect because of what they call the golden rule. I think it's what it is, something like that. It's that the ratio of the length to the height is just a perfect number. And in fact, remember, I'm not going to model it completely, but Da Vinci had the man standing in a circle, his hands and arms, his dimensions. In fact, most of the greatest art and architecture somehow have Fibonacci sequence involved with it. Okay? They show in your book a sunflower center. And look at that. Look at the pattern that you get as you move out from that. If you were to count the things and follow the spirals out, you're going to follow Fibonacci sequence. What's that? What's that? I heard the out of that. I couldn't figure out the rest of it.
How does that go with measurements? How would you measure something like that?
They sort of give the illustration here. I said the golden rule. It's the golden mean. I forgot that. Okay. If you were to, let's say, take the limit of the n plus first term divided by the nth term. Okay? Let's just do a few of those. I don't know if I did it right. 144 divided by 89. See what that gives you. 1.6. Okay, say that again. 1.6179. Okay. How about 89 divided by 55? Okay. So you see they're awfully close to the thing, and that is what they call the golden ratio. 1.618 is not known as the golden mean. Okay. Okay. It follows that pattern, and it's just incredible. I mean, it's so pleasing, and the human body is basically put together that way. I can't think of all the things, but the ratios of things for to be aesthetically pleasing, they always are going to follow very, very close to that golden mean. Okay. So something that's purely mathematical here turns into art, turns into architecture, probably music. I mean, there's probably an infinite way, and certainly the sunflower. If you do the ratio of that, you're going to wind up with that golden mean just about every time, or something awfully close to it. Okay. All right. I did get the first few right anyway. I don't know if I got the last one. Let's look at example 2. This is a different kind of sequence, and this is a what they call a recursive sequence, and they give you the first. So let me clear this. All right. A1 is equal to 1. They give you the first one. Then they give you the sequence after that, or this sequence after that. A sub n is then going to be 1/2 of A sub n minus 1 plus 2 over A sub n minus 1. Okay? So what would be A2? 1/2 of your n is 2, right? So n minus 1 is 1. A sub 1 is 1. Okay? So that would be 1 plus 2 over 1. So that would be 1/2 of 3, which would be 3/2. Right? You buy it? Okay. What would be A sub 3? 1/2 of, second, 3/2 plus 2 over 3/2, which would be 2 times 2/3, right? So it'd be 3/2 plus 4/3. That would be least common denominator of 6. That would be 9 plus 8. So that would be 17/6, and 1/2 of that would be 17/12. You see that? Okay. All right. I want to go much further, but you can see you can keep going. A sub 4 would be 1/2 of 17/12 plus 24/17, right? Because you invert this and multiply it by 2. So it'd be 24/17. Whatever that comes up to, take half of it. Get to be really ugly fraction, really fast. Okay. So next was 17/12, next was 577 408. But then look at what your the numbers are doing though. What is that? 1.5. The next one's 1.4167. The next one's 1.414216. Goodness, it looks like they're converging, doesn't it? Right? Does that look familiar? 1.414? The square root of 2. Isn't it? I don't know if they ever tell you that. But it sure looks like it's going there to me. Yep, there it is on the margin. You see on the margin? That little note there. You may recognize the sequence in example 2 as a sequence of approximation of the square root of 2. 1.414213, blah, blah, blah. In just 4 steps, you got 4 digits, 5 digits, 6 digits. Okay? In just 4 steps, you had 6-digit precision there. Okay? Sequence of approximation of the square root of 2 produced how? By Newton's method. Goodness, that guy was in on everything, wasn't it? Okay? He developed calculus, and yet he came up with ways to estimate the square root of 2 using, now, like I said, he was right in here. He did integral calculus, differential calculus. He did sequences.
Social life was like
Miserable. He was an ornery character. He didn't get along with people well at all. Some people think that he was really psychologically scarred by the fact that, okay, number one, his dad died before he was born. His dad died while his mother was still pregnant. So he never knew his father. And shortly after he was born, his mother remarried, but the new guy didn't want anything to do with the previous guy's kids, so Newton got sent to the grandmother, rejected by his mother then. His dad died, his mother rejected him. Later brought him back in, and they tried to make him into something he wasn't. Tried to make him a farmer, not the best farming material, you know. And so he was pretty miserable, I think. And he was very poor. He went to Oxford, I think it was, Cambridge or Oxford one, I can't remember which. He was so poor, but he was so brilliant, but he was so poor that he had to wash the other students' clothes, shine their shoes, you know, iron their undies. I don't know what all he did, you know, but he was treated like a servant. In about 3 years at Oxford or Cambridge, whichever one it was, I can't remember which, he passed all of his professors. They couldn't keep up with him. And they said, look, can you take this? One of them said, look, I'll resign my chair. Will you become the chair of mathematics, you know, because he was, as soon as he got exposed, his mind just crazy.
He was born prematurely.
Yeah, and he was a preemie too. He almost died. Back in that day, preemies that age did not live. He did survive. Yeah, it was, yeah, what were you going to say?
Like too smart for his own good. Like,
Yeah.
he was just, it would be hard to have a social life if you're that smart.
Yeah.
I feel like your mind's so far ahead, like everybody else that they don't understand.
You hardly have any peers, is basically what you're saying. And the closest you got are this far away, you know. And then he did a lot of work at alchemy too, and probably got exposed to mercury and lead and other things that they didn't know were harmful at the time, and he may have actually messed himself up that way too. But he still lived to be, I think, in his upper 70s or 80s, which for that day and time was incredible, especially for a preemie, you know.
It also says that his dad was a farmer and his mom was like, his mom barely could read.
Was what?
His mom barely could read. So his parents were basically like dumb. Or not dumb, but poor educated.
Yeah. My father was a farmer.
Hey, my dad is too. So
yeah, okay, good.
My dad was since we got here.
Are you proving your point or just, no, never mind, okay, never mind. Okay.
My dad was a farmer and he only finished elementary school.
Mine finished college, but yeah, he still wanted to farm. He didn't want to work for anybody else. He was a stubborn old cuss. Okay. All right. In fact, he was an ag engineer. That's where I got my math. All right. Enough of that, huh? Wait a minute. Oh, I've already given the limit of a sequence. I was saying they didn't have the definition of a sequence. I failed that. I thought that was the definition of a sequence. That's the limit of a sequence. A sequence is an ordered collection of numbers defined by some function on a set of sequential integers. The values a sub n is equal to f sub n is called the terms of the sequence. N is called the index, meaning which one you're talking about. Informally, we think of a sequence a sub n as a list of the terms. The sequence does not have to start with n equal 1. It can start at 0, 2, or any other integer. Most of the time doesn't start with negatives, but it could. But usually 0 or positive. How are we doing on time? I saw you look good. We still got it. Yeah. Yeah. I know. I need to keep up too because it's sort of a wacko day. My last class went really long. Okay. All right. We've already done this slide then, limit of a sequence. Okay. That's where we get here. I was just skip. Now, this would be a sequence. I don't know what term that would be, but this would be a sequence. Starts with a lot of divergence here, okay, all over the place, but after a while, you get in here into the zones here, and once you're in there, you never leave. Out here, you weren't in it, okay, but somewhere out there, you did get within it, and you never get outside. And in fact, somewhere down here, you can make your zone smaller, and you'll never get outside that. And that's what makes the sequence, okay? Here's a plot of a sequence with limit L. For any epsilon, they happen to choose the one with the green bars there. The dots eventually remain within the epsilon band. It looks like they could have chosen an epsilon this big. And after a while, they all stay within that. And maybe out there it could have been that big, you know, and after a while, I mean, it's almost you're approaching, getting closer and closer to that L. That's how you can think of a sequence. These are individual points. These are members of a set, not a sum. That's a series, a set. All right. This is a much more orderly one, okay? Here is this one. The sequence of n plus 4 over n plus 1. Now here your n could start at 0. It could start at negative 1, right? Okay. Don't even go there. Could start at 0. At 0, that would be 4. Okay, they don't show that here. That would be way up there. Okay? But at n equal 1, that would be 5 halves, right? Okay? That'd be 2 1/2. That's not even shown here. Okay? So I don't think this is quite right. Okay? N equal 2, this would be 6/3. That would be 2. So this isn't right. This is not the sequence. There is illustrative of it, but it's not. They've got the thing all wrong. Okay? This is 2.5 right here, it looks like to me. That's 1. This should be 2.5 there. Okay? But anyway, you get the general idea, but the further out you get, the closer and closer you get to 1. Now again, use that little trick that I did. What's the limit of that? Well, let's divide numerator and denominator by n. This will be n over n, which is 1, plus 4 over n, which is 1 to 0. As n gets larger, 4 over n goes to 0, right?
You said divide by n?
No. Multiply. No. You divide numerator and denominator by n. Okay? So that becomes 1 over 4. 1 plus 4 over n, which is 1 to 1. This is 1 plus 1 over n. 1 over n is going to 0, so that's 1 to n. N over n is, 1 over 1 is 1. So that's the limit of that sequence. That's not the right y values there, but it's the, see, does your book do it better than that? No, your book still has it wrong. Sorry about that. Now, here's another sequence. Now, that certainly stays within the band of +1 to -1, but does that ever converge? No. Now, what sequence is that? A sub n is equal to cosine n, where n we'll have in radians now, and just pick, 1, 2, 3, 4, 5, just do all those. Cosine is always going to be equivalent +or -1. So it's always going to be within that band, but it never converges to anything. Because it just randomly goes anywhere within that band that it wants to go to. So that is not going to infinity. It's not unbounded. It's bounded, but it never converges. Okay? So you can have sequences that have no limit, but that doesn't mean they go to infinity. They can just bounce around randomly in between two numbers and never go anywhere. All right. Now they have a little thing on proving convergence here. And I've really already done what you need to do here. But I did it a lot easier than what they do. So I'm going to skip example 3. We just don't have time for it. Read through it. It's actually a formal, very good proof, but it's not the easiest way you can show that. But anyway, let's move on to theorem. Whoa. Well, yeah. What in the world is that?
I think I learned this in trig.
What's that?
I learned this in trig.
You did what?
I learned that in pre-cal.
Oh, you did?
I think so.
Okay, was this up at Huntsville? Or here?
Huntsville.
Okay. Yeah, I was going to say, we don't usually do this in pre-cal on this camp, here at Lawson. So if you did do it here, I was going to say, who was your instructor? Okay, that y'all got that far. But I wouldn't be surprised because calculus, one of the branches of calculus, the infinite series, we usually focus on the other branches, the algebra and trig, parts, but sequences are part of it. If you look at your pre-calculus book, it has infinite series in it, series and sequences. Okay, here's one. If f of x converges to L, whatever that L happens to be, then the sequence a sub n equal f to n also converges to L. Now what they're getting at, and we're going to get to that in a little bit, in fact I think the next slide, when you're starting off it can be way off from L, but over time it's getting closer and closer to L. It may go up and down, up and down. It doesn't have to alternate up and down everything. It may do that kind of pattern, but it also converges. And here is the theorem that supports that. All right. If the limit as x approaches infinity of alpha of s exists, then the sequence a sub n, which is f of n, converges to that same limit. So that's taking a continuous function, f of x. That's a continuous function. If that limit exists, then a sub n, which is f of n, that's not continuous. This is discrete. Your n is 1, 2, 3, 4, 5, where the x can be 0.738, 0.738, 777, it's a continuum there. Here your n's are integers, not continuous, but integers. But then this so if that one converges, this one converges too. So the limit of a sub n, which is f of n, is the same as the limit as x approaches infinity of f of x. Okay, so you go from a continuous variable to a discrete variable here, and those are going to be the same. Okay. Yeah. So let's do some. Okay. Find the limit of some sequences. Here's a sequence. 2 squared minus 2 over 2 squared. 3 squared minus 2 over 3 squared. 4 squared minus 2 over 4 squared. 5 squared minus 2 over 5 squared. It keeps going and going and going. The Energizer Bunny. Whoa! Okay. Do I want to plug in those numbers and do those calculations? Try to figure out what that is? I'd rather not. Yeah, I'm too lazy for that. Okay? So what we do, that is basically this kind of deal. Let's see if we can get it into a deal like that. What is this? What is our A sub n here? N squared minus 2 over n squared. Now, you know that little trick I told you? Divide numerator and denominator by the maximum exponent of your n. So this will be n squared over n squared minus 2 over n squared over n squared over n squared. Pretty exciting, huh? Okay. All right. What's that first ratio here? N squared over n squared? 1 minus 2 over n squared. What would that go to as n gets bigger and bigger and bigger? 0. Over n squared over n squared? That looks like it's a 1, doesn't it? Now, I'm not sure if I just looked at that to begin with, I would have ever guessed that would come up to 1. You did. Oh, good for you. Okay. Now, let's do some of this. This would be 4 minus 2 is 2 over 4. That would be 1/2. That I wasn't going to do this over. 9 minus 2 is 7 over 9. 14 over 16. Which is 7 over 8. Okay. 23 over 25. 36. 34 over 36. Yeah, that's getting closer and closer. But you saw it. Okay. All right. See how that works? Now, that's one way to do it. That was my little trick. Here's another way. This one's probably easier with this one because this can be done this way. That is n squared over n squared minus 2 over n squared. That's even easier, which is 1 minus 0. Okay? Because that one, you had a monomial in the denominator, that makes it so much easier to do. I did it the hard way, okay? But I'm used to doing them when they don't have monomials in the denominator. That way will work then. Okay. So there are some ways to do that. All right, let's move to example 5. And that's not here either, so let's, whoops, wrong one. Calculate the limit as n approaches infinity of n plus log n over n squared. Okay? Uh-oh. What will we do with that? Yeah, n squared plus log n over n squared. Sorry, my writing's pretty bad. Make fun of me, I don't care. Okay. It doesn't hurt. Okay. I'm used to it. I'm calloused. Okay. See the little name that rings a bell there? That's a form, that's a ratio that your numerator is going to infinity and your denominator is going to infinity, right? Okay. Say again? We don't know. Let's see. You remember a little technique we used when you had infinity over infinity? Does the name L'Hopital ring a bell? Not really, huh? Yeah. Okay. L'Hopital, another pretty fascinating character there. Some people claim he's getting the credit for it, and he didn't really deserve it too much. He studied under one of the Bernoullis. I don't know if you've run into Bernoullis, have you? Oh, you should have. Okay. The Bernoullis were a family, I think they were Swiss mathematicians who were brilliant. And sort of in the, not maybe quite the level of Newton's brilliance, but they didn't get along with people too well. They didn't get along with each other too well. There were two brothers, Johann and Jacob and Johann, John and Jacob, yeah. And I think they competed like crazy, and they had kids. I know some sons, maybe some were cousins or nephews, I don't know what. And they competed with their fathers and with others. And one of the dads had entered a contest and knew he was going to win the prize because he was the sharpest mathematician in Europe at the time. And then somebody beat him. You know who beat him? His son. And you know what he did? Oh, I'm so proud of you, young man. No, he kicked him out of the house. Okay, you steal my prize from me. Get out there. You're on your own now. I mean, they were sort of dysfunctional family. But anyway, I think this guy L'Hopital studied under one of the Bernoullis, and the Bernoullis taught this, but they had never written it up. So L'Hopital wrote it up and got credit for it. You think some old professor who was really angry at that? Okay. If I'm not mistaken, that's what happened. But here's what L'Hopital's rule says. If you have a form that's infinity over infinity, also 0 over 0, infinity minus infinity, any of those kind of forms, what you can do is take the derivative of the numerator and the denominator and try it again. So let's take the derivative of the numerator. What do you get? 1 plus derivative of log of n. 1 over n. And, okay. Over 2n. Okay? Now I'll take the limit of that as n goes to infinity. What's the limit of 1? 1. What's the limit of 1 over n as n goes to infinity? 0. So that's 1 plus 0 is 1. What's the limit of that as n goes to infinity? Infinity. So you have now 1 over infinity, which is going to 0. Not 1. Okay. But you knew. Okay. Okay. Close, yeah, within 1. Okay. All right. Okay. So that one's going to 0. Okay. Now, I don't know if you want to get my little take on that. The graph of f of x equals x is that, right? The identity function, right? Okay. Log doesn't go up as fast as the identity function, right? But n squared goes up faster. So here you have something that's smaller in the numerator with something that's bigger in the denominator. As n gets bigger and bigger, that's what we're going to see. Okay. It sure has all the indications of that, right? Okay. That's just my little way of looking at it. And sure enough, that goes to 0. Okay, how are we doing? Oh, yes. Okay. Now we go to the Balmer wavelengths. These are the ones we looked at before. The history of the Balmer wavelengths, this is B sub n, and the next example plays a role in physics and chemistry because it determines the ionization energy of the hydrogen atom. Okay? This was way in the very beginning of quantum mechanics. Okay? I think this was called the Bohr atom. Okay? Niels Bohr came up with this as his first approach. Worked quite well for hydrogen, never worked for any others. Okay? But it was historic, folkloric, and everything else. Okay? And these are your Balmer wavelengths. And remember that formula we had before, where it was 650 something, 0.2.5 or something, 364.5 n divided by n squared, something else. These are your Balmer wavelengths. N is equal to 3. It works for 2 because it was, remember, it was n squared minus 4 in the denominator, right? Couldn't do it 2. Okay, so you had to start with 3. And that gave you, I'm pretty sure that's a violet wavelength. This would then be a red, maybe, or an orange or a yellow, something there. Then you're getting down into the reds. But you see, these get so close together you can't tell. You can pick out, I think, the first 3 or 4 of those, and after that, it's sort of goes. It gets so close together you can't tell any separation. Okay. So really, we only use at most, I think, 4. Okay. And in this, again, calculate the limit for the Balmer wavelength where B sub n, and this is the one we did before, 364.5 n squared over n squared minus 4. And this is where I think I first told you about the pretty easy technique to do is divide the numerator and the denominator by the maximum power of your n. So this would be 364.5 n squared over n squared over n squared over n squared minus 4 over n squared. Okay? And this, of course, goes to 364.5. That goes to 1, and that goes to 0. So you get 364.5, not 6, but 5. Okay? So that is the limit. Make sense? Now they change it to a function of x and then do strange things with it. Just divide by n squared. I haven't quite figured out why they did it the way they did. All right. The next concept here, are we going to have time? Yeah, let's do it. Is, okay. That's the Balmer series, okay? Yeah, that's the graph up at the top, figure 7 in our book. It's figure 6 in this one, okay? This is graphing that Balmer series. Okay. The first one up in the 600s, next one down in the 400s, and then you get closer and closer to the 364.5s. And again, you can pick out a distinct wavelength, a spectral line there, and I think you can usually see this one. After that, they all merge together. You can't see it anymore. But that's usually what we deal with in the Balmer series. Now, here is on the color scheme, and this is what I was trying to get to before. Oh, I said them backwards, didn't I? Okay. The 600s were the reds, and then you had the greens, and then you had a blue and a violet, I believe, is what you can pick out. Down here you can't distinguish anything else, but you can usually pick out those first 4 spectral lines. After that, they all merge together. What's that?
blue, indigo, and violet.
Yes, well, indigo they threw in there just to make it say div. Okay.
Is ultraviolet dark or light?
What's that?
Is ultraviolet like more black?
Oh, no, it's not black. It's something we can't pick up. You know, it's beyond violet. Okay, red, orange, white, yellow, green, blue, indigo, violet. Past that, we don't have receptors to pick up ultraviolet. Okay.
What color is it?
It's not a color. You can't see it. Okay. In fact, it can do damage to your eyes. That's ultraviolet is what gives you sunburns. Ultraviolet is what gives you cataracts in your eyes. You live long enough, you're going to have cataracts because ultraviolet radiation does. Ultraviolet basically is what ages you. Gets you all these little spots on your face, you know, and skin cancers and things like that. Ultraviolet is actually harmful radiation. That's why you big on sunglasses. Okay. What's the best kind? UV protection. Huh? What do you say?
Polarized.
Yeah, polarized are good, and also UV protection. You know, and it's UVA and UVB, two different ultraviolet. You're wanting to protect your eyes to keep you from getting cataracts. Okay, so that ultraviolet radiation will destroy tissue over time. That's what a sunburn is. You're burning the tissue, you know, and you might say, well, but I like having a tan. Well, your tan is your body's trying to defend against that harmful radiation, so it sends extra keratin, I believe it is, to the pigments of the skin, trying to protect and keep that from happening. And some of us have more natural than others, and so therefore you don't have as great as skin cancers as some of us others do. Yeah. So count yourself fortunate.
I don't wear sunscreen when I go to the beach.
What's that?
I don't wear sunscreen when I go to the beach.
You don't?
Actually, every time I do wear sunscreen, I get more burnt than when I don't wear it.
Really?
So I just don't
It sounds like you're allergic to it, is what it is.
possibly.
Yeah.
I've tried different ones, and every year that I go, I get burnt. I'm like, so last year I didn't wear anything at all.
You should, because it's indecent. I mean, okay. Yeah. Okay. All right. So that gets you through the Balmer series. All right. Here's the other. Are we going to have time? Ooh, we really don't. But let me just introduce you to it. Okay. This is the geometric sequence. This is a pretty important thing in just about everything. The geometric sequence. What it is, your A sub n is equal to sum C R to the n. Okay? And what it means that for the next term, you just multiply it by that same ratio. So in other words, the ratio of this to the previous term is just going to be R. That's what a geometric sequence is. C is a non-zero constant. R is a non-zero constant. Each term is R times the previous term. Every time. A sub n divided by A sub n minus 1, always equal to R. That's what R is, the ratio. And you go up by that ratio every time. Give me a number, any number in the world. 7. Okay, give me another number. 8. Okay, so 7, 56, 8 times 50. You had to give me a hard one there. Let's do 2, okay? 7, 14, 28, 56. What's the ratio of every one of those numbers? This divided by that. This divided by that. 2. The ratio is 2. The 7 is just that C, wherever you begin, and then multiply it by that ratio 2 every time. could have chosen 3 as the first one. It would be 3, 6, 12, 24. That's another geometric sequence. It just has a different C, same R, same ratio. Okay. Or that could have been 8. I just can't multiply 8 times 56 very fast. Okay, so I could do it, but it's just not very fast. All right. Unfortunately, that's all the time we have. Sorry, team. Let me run off your copies.